jump in a few minutes early, not covering anything essential, but I thought you guys might kind of enjoy. This morning, I also did tweet this out. This is just a really neat image of the Ebola virus actually budding off of an epithelial cell. And so I thought I would just show you what the virus looks like. It's the kind of orange, reddish looking guy right here, and it's actually a virus in the family Filoviridae, and philo actually means thread. So it is shaped or looks like a thread, like a long kind of helical shaped virus. So that's the look of the Ebola virus. And once again, following me on Twitter, this is an image you'll find on there, and you notice that Taylor already put Go Kochs on there. Must be already following me on Twitter. So that's fantastic. And I also wanted to point out one other thing. On YO courses, some people have certainly asked me about where they're going to access the VODcast that I post from lecture. So should you miss a lecture, or better yet, should you want to go back and re-listen to that lecture, this is where you're going to find that. So notice that I clicked on modules. That's, of course, where you're finding your homework. But it's also where you're finding the optional book discussion, the pre-test knowledge survey that is also optional, but is worthy of some incentive in regards to replacing your low homework. But then notice at the very bottom, you're going to see something called VODcast. And you click on that, it'll take you to a page that will have the VODcast from Wednesday's lecture. So I've already uploaded it onto YouTube, and you can already get in and watch Wednesday's lecture. If you wanted to review it, there was just something you felt like you didn't get good notes on, you can go right into YO courses and find that there. So that's just a little bit of an overview on a few questions that I've gotten. And so now that we're actually getting towards time, I'm going to jump right into our coverage for today. I wanted to let you know that I enjoyed going through absolutely everyone's note card. It's probably one of the things that I look forward to the most each semester, and getting to know you. I picked out just a few quotes because I thought they were particularly memorable, and although they were not the only memorable ones, here are just a few that I will share with you today. So the first one came from Kevin, and he said he's just simply passionate about the joy that women bring to his life. So Kevin, where are you here today? Absolutely, I'd rather not raise my hand. I don't want to incriminate. This one was particularly good. And is it Andre? Is that correctly pronounced? Are you here? Not incriminating yourself? Oh, come on. With a note card like this, you'd want to incriminate yourself. Maybe he's not here. So this one was kind of funny because fine Oriental soups and fighting dolphins. So I'm not sure whether he likes the dolphins fighting amongst each other or whether he likes to fight them. But one of the two. Andrew is passionate about the outdoors. He says enjoys hiking, biking, swimming, tennis, rock climbing, fishing, camping, nature photography, kayaking, music. Also enjoys nutrition, reading, and studying medicine. So this is like the true Renaissance man. So Andrew, are you here? No. Also not incriminating himself. So this one was beautiful. Kindness. So passionate about kindness. I don't know if that counts as an activity. I'm just very friendly, and I'm always up for doing some fun things with people and meeting new people. So Ariana, are you around? There she is. Of course that counts as an activity. The best kind, I think, for sure. Thank you. And I think Anne is here somewhere. She says dancing, especially ballet. She's also passionate about medicine, orthopedics. Surgeries are amazing. She's currently enjoying the Game of Thrones book series. I got a chance to listen to Game of Thrones when I was driving across country. Well, actually, I wasn't driving. I was primarily grading student work the whole time. So I'd put my headphones in. The people in my car were listening to it on audio version, and so I'd put my headphones in, grade for about 5 hours, and then I'd take them out for a little while, and I didn't miss anything. And so that was fun. I feel like I've experienced Game of Thrones as well. Oh my gosh, Harry Potter, and her favorite color is pink. So is that the Anne that I was talking to yesterday about I fucking love science? Was that you? Yeah, that's you. Okay, yay. I love it, Anne. Beautiful note card. And then Cassie asked me if I'm always so hyper. So my answer for that, Cassie, where are you? My answer for that is that you'll just have to come to class every day and find out. Wait and see. So those were just a few of the awesome passions that were shared on your note cards, and I really did love all of them. A lot of great definitions for bulimic learning. I thought a nice succinct one was given by Brent. He says, learning long enough to take a test, then you regurgitate the information onto the exam, just long enough to get it down on paper, and then you dump the information and you replace it with the stuff that you need next, right? No connections are being made, and you're not able to teach it to someone else. And that, I think, is a really poignant definition. I remember taking organic chemistry, and man, I rocked that class. I was so stoked. And then I got asked if I would be an OChem tutor, and I was like, woohoo, yeah, OChem tutor. And the first student that came to me for tutoring, I said, wow, I don't remember this stuff. And I didn't remember anything well enough to teach. And that was a really great knock in the head for me to realize that the way that I was learning needed to change so that I could teach it. And so that's where I'll challenge you all. I hope to see many of you teaching each other this semester, because really that's where the deep learning does derive, is in teaching one another. I liked what Kristen said as well, learning without the intention of retaining anything. And what I liked about that is that she's actually stating that sometimes we literally go into the learning experience without any intention of taking something away from it. I can't tell you how many times I hear a student say, you know, I don't care about that class because it doesn't pertain to my major, and so I have no intention of learning anything in that class. And the really sad thing about that is that truly all of knowledge is integrated. We're the ones that put the barriers and the boundaries and the silos on learning and education. And so really all things are related to one another. All things are really integrated. So Kristen and I like that a lot. Learning as a temporary technicality, learning as a hoop to jump through. So only getting just enough to get the A and then moving along. All of these were great definitions for bulimic learning. I didn't get one that I felt put the instructor's responsibility out there, so I'm using one from last semester. This definition says, the type of learning common in college settings where huge amounts of information are fed to the students and they are expected to vomit it back to the teacher. This is great because what this definition does is put a bit of the onus on me, as it should. Because if I simply get up here every day and I use the empty vessel theory of learning, meaning that I see all of you as these beautiful vases that I'm just going to puke into, and you're going to fill up with information, right? You're going to leave and you're going to carry away everything I said. Common misnomer for instructors, right? We commonly confuse covering lots of content as equaling student learning, and it does not, right? It does not. So you will all, I hope, hold me to that. So if I start projectile vomiting at you at any moment and you're like, oh my God, I'm not taking any of this, stop me and say, could you re-say that in another way? I don't quite understand where you are. And chances are that if you're bold enough to say that, there's somebody sitting next to you who also doesn't understand a thing that I just said. So feel free to do that. Absolutely do. Lastly, I thought I did a nice job of actually relating deep learning rather than bulimic learning. Deep learning is sort of the opposite, being able to learn something that you then can teach to someone else. That being said, I have a few reminders for the up-and-coming events. And I know it's Friday, so feel free to just shout out at any moment. It's Friday. But I do have a few things of serious note that we need to think about. Remember that pretest knowledge survey I just showed you on Wild Courses where you'll find it. If you would like to be able to replace your low homework score, go ahead and get in and do that pretest knowledge survey. Ellie was asking me today whether or not you could do that in multiple settings, like you could get in there, do a little bit, come back, do a little bit. you actually can't. The way I have it set it now, probably want to go spend an hour on it and see what you can answer. Some of you, if you're very advanced, if you are seniors, you may find yourselves being able to answer more questions and it might take you a little longer. If you get into trouble with the time frame that I've set there, just holler at me and I will reset it for you. Remember that this is optional. It is completely up to you as to whether you do it, but it does give you a kudo as far as that low homework score, and it also helps me as far as assessing student learning. Homework 1, how many of you have found that already, downloaded the PDF? You have it with you today, perhaps. Excellent. You guys are rocking my world. Absolutely good. And somebody next to you at least has it, right? So they can do the homework for you, and then you can give the answers later. Good deal, right? So at least you've got that going on. Bridger's got it rocking. I promised this. If you've got a scrap piece of paper with you, pull it out, or if your neighbor has a scrap piece of paper they're willing to provide for you, sell to you, then please just grab one out. And let's go through a quick extra credit quiz. If you throw this my way, hey, put your name on it so I know who you are. I will give you some extra credit points. So how about this? Current events poster project. True or false? Poster presentations will occur during our regularly scheduled final exam time. True or false? Don't shout it out, just write it down. And number 2, finalized posters should reference one journal article and one public perspective article in total. True or false? 3, a draft of the finalized poster is due before you get your take-home final exam. And lastly, true or false, the assignment description outlines and gives examples for 2 types of hypotheses, observational and quote-unquote pseudo-manipulated. True or false? I'm not actually going to grade these, but if you hand a paper up towards me, towards the front, then I will give you extra credit, absolutely, and you'll start with a little padding. You guys can collect them and then get them up here. Just throw them towards the front, And if you don't get them towards the front by the end of the hour, bring them up here and throw them on the stage just like you did with your note cards. So hopefully everybody is getting wicked jazzed about the posters. I actually heard Amy say that she spent a little quality time researching some potential articles and topics. Absolutely fantastic. I hope a lot of you have started to dork out with that. Today, I tweeted out also on this, fascinating, every day another connection between the health of the human microbiome and our health. This one talked about the link between liver cirrhosis and the health of the microbiome. So another really cool link to be talked about there. So on Tuesday, we will have lab, and your pre-lab number 1 is due. Who was it that brought up to me there was some relic feature on there that said lab was canceled? Either that, it was one of the TA's practical jokes. But I deleted that. We do have lab on Tuesday, so I'll see you all on Tuesday. Okay. Questions? Yeah.
Yesterday they were out of the lab manuals, and
yeah.
They said that they were copying them. I haven't gotten a call or anything said that they've had it yet.
Okay, yeah. So, we'll just keep our fingers crossed. How many of you haven't yet had a chance, or haven't gotten the lab manual because they didn't have enough copies of it? A number of you. Okay, yeah, good. So that's fine. If you don't have them on Tuesday, just make sure you come to lab with bells on, and I promise we'll take care of you. One of the things that I can do is put a copy of Lab 1 up. So, Megan, is that right? No? Yeah? What? Yeah? Okay, Megan, would you take responsibility for emailing me if on Monday you don't see any sign of them coming in, and then I'll make sure you guys are, I get a copy of that lab to you. Perfect. Yay. Any other questions, thoughts, concerns? Random outbursts. It's Friday. Okay. Harry Potter rocks. Perfect. I like it. Fantasmic. When we left off last time, we were in the heat of a debate. We were trying to decide who was going to win the argument between Esteban and Amy as to how long ago scientists firmly put the nail in the coffin of spontaneous generation. And we had just confirmed one of Amy's thoughts, and that was that Louis Pasteur did this rad experiment with the swan-necked flask where he had broth in the flask, and he exposed it to air, but only through this nice swan neck. And because of that swan neck, all of the dust and microorganisms settled out in the first bend of the flask, therefore allowing air to enter into the broth, but not microorganisms. And in that way, he was able to show that in the bend of the neck, microorganisms had been present in air, but that air itself did not cause what? Spontaneous growth out of nothing, out of absolutely dead matter, nothing popped up. And for years, that flask would stay sterile until Louis Pasteur did what? Broke the neck and allowed those microorganisms to land in the broth. Now, we ended with this idea that if things were to then go well, other scientists would be able to do what? Repeat Louis Pasteur's work. Now, Amy didn't realize it at the time, but she came up with something ingenious when she said, I can't remember what kind of broth he used. Well, it turns out that that was the miscommunication. Other scientists also couldn't remember what kind of broth Louis Pasteur used, or said another way, they didn't pay attention to what kind of broth he used. And so they tried to use other kinds of broth. Now, he used beef broth, but other scientists said, oh, I'll use hay broth, right? Hay broth, meaning they would boil hay, and that would be the nutrients in there. Can anybody think of something that would be different about hay as compared to beef? Yeah, maybe the nutrient composition, right, Lauren? I mean, that would be, that's right, isn't it? Okay, maybe that would be what was different in there. What else? What about the types of microorganisms that you might find in beef broth versus that in hay broth? Hay comes from what kind of environment? Yeah, Lauren.
Heat-resistant bacteria.
Yeah, excellent. So on hay, which is very much exposed to dirt, there are a lot of bacteria that are like, when the going gets tough, I get going, right? They are called endospore-forming bacteria. So what they do is when the going gets tough, they roll into these resistant dormant structures that don't mind being boiled for a little while. They're not present in beef broth, but they are present in hay. So other scientists couldn't repeat Louis Pasteur's work because they were trying to use broth from other things that had these heat-resistant bacteria. So Louis Pasteur, he needed some help, right? Because he needed someone to come on the scene and show why it was that his work could not be repeated. And that onus fell to a man named John Tyndall. Now, John Tyndall was very famous at the time, or at least his high horse at the time, was looking at the correlation between dust and disease. He was getting to this idea that dust carried something in it that could cause disease. And we now know from Louis Pasteur's work that that was microorganisms, right, that were found in the dust. And so this particular article, I want to share a passage out of it for you. It's the British Medical Journal, and this particular one was published in 1871. And I'm reading to you from a lecture that John Tyndall gave. And it's fascinating to see that he was definitely fighting on the same side of the debate as Louis Pasteur was. So here's his quote. You know that as regards the lowest forms of life, the world is divided and has for a long time been divided into two parties. The one affirming that you have only to submit absolutely dead matter to certain physical conditions to evolve from it living things. The other, without wishing to set bounds to the power of matter, beautiful, right? Affirming that in our day, no life has ever been found to arise independently from pre-existing life. Many of you are aware that I belong to the party which claims life as a derivative of life. Love that passage. Right? Essentially what he's saying is that he believes in biogenesis. Isn't it interesting to think about how maybe that kind of thing might parallel some of the debates that we currently have, where one party of people believe one thing and one party of people believe another thing? And we think it's funny now to think that what they were arguing about is whether life comes from other life. But clearly, this was a big thing. This is a big thing. And so John Tyndall, what he did was he was able to show that different kinds of media require different boiling times in order to truly be sterile before you could repeat Louis Pasteur's work, right? And that was one of the contributions that he made to this fierce debate of two parties, the biogenesis party versus the spontaneous generation proponents. Later on, a man named Ferdinand Kohn came onto the scene, and he actually gave a name, he kind of found and was able to identify that what Lauren said was the heat-resistant bacterium. He was able to show that there was a form that it would convert into this heat-resistant form whenever the going got tough. And so later, these were called endospores. And so at this point, we get to put an end to the Esteban-Amy argument, and we can see that despite the fact that probably Esteban should have been right? Really, people should have realized with the early work of Francisco Redi that spontaneous generation just wasn't a thing. They didn't. Right? They did not realize it, and it wasn't until later that they finally were able to fully disprove that notion. So I brought with me today an epic giant stuffed microbe for Amy, and this is a typical cold virus. It happens to be wearing a Santa hat too, but you know, it's yours. So congratulations, debate settled. 138 years ago. Now, I want to talk to you a bit about what happened after that, because after after the work of John Tyndall and Ferdinand Kohn, it turns out that Robert Koch came onto the scene, and what he was able to do was a new idea, right, of showing that a particular bacterium caused a particular disease, right? So I want to see if we can derive his set of postulates, right? If you wanted to prove to me right now that a particular bacterium causes a particular disease, what are the things that we would have to do? So we're going to derive Koch's postulates one at a time, telling us what would we do? What would be the first thing that we would do if we wanted to prove that Bacillus anthracis is the bacterium that causes anthrax? Well, while you're thinking, why is anthrax so famous? Come on, guys, we're real close to the anniversary. 9/11. And what happened shortly after 9/11? You remember? Anthrax. Yeah. The white powder, right, that was inhaled. It was actually highly purified anthrax spores. So it's kind of interesting to think about the fact that we, even at that point, didn't have a great way to deal with that, even though this was shown to be the causative agent of anthrax in 1876. So kind of interesting to think about that. Go ahead, you got to, yeah.
The first thing we need to do is be able to extract the bacterium from the infected organism.
Right, good. So in some ways, we might call that number 2 in that we might say that we really need to be able to isolate the bacterium from an infected host. We want to get it in pure culture, and here pretty soon in the lab, you guys are going to be doing that. You're going to be isolating bacteria in pure culture and seeing how that works. So that's a huge one. Now, where do we want to know that the bacterium is present, whereas where do we want to know it's absent? Yeah, perfect. So we might just say, no, it's great, it's perfect. So we might just say something like the bacterium should be observed to be present, and I'm just going to write bacterium present in all sick hosts but absent in healthy organisms. Bad G, sorry. Organisms is that last word. I just abbreviated it. So yeah, that could be seen as Koch's postulate number 1. So now that we've isolated it, so we've gotten through the first 2 here. Now that we've isolated, what do we need to be able to do next with it in order to fully prove, right, that it causes the disease? Yeah, Bridget. Yeah, infect a healthy host and see what? The disease, right? So now take the isolated bacterium and use it to infect a healthy host. And I'll just do an arrow. See disease symptoms, right? The disease ensues. And then for good measure, what should we do last? Yeah, Stan.
Try killing the bacterium, and when trying to infect a healthy organism and seeing if they cause the disease or not.
Okay, I like that. That's kind of a control experiment, right? Where you're looking at a neutralized situation. Is that what you're saying? Yeah, I like that. And I actually think that could be nicely added as a control group. It's not a part of the original postulates, but I do like it a lot. How about just from this healthy host that we infected and saw disease, re-isolate it? Yeah, the last one is really just simply re-isolation. Now, okay, so these are the original postulates, basically, as you guys have come up with them. But we can say now that there are some nuances here that maybe could be debated. For example, we know better that the balance between disease-causing microbes and healthy microbiome microbes is a tentative one. And many of us harbor Staphylococcus aureus. It's one of our characteristic microbiome organisms. The key to it not making us sick is the balance between it and other organisms. So there are nuances there that Koch didn't propose at this point, and we could add to these. But I will tell you that modified postulates are still used when trying to decide if something is causing disease. So this is an interesting ending, if you will, to that story in 1876 when these endospores were found. And interesting to note that the first disease-causing pathogen for which this was done was Bacillus anthracis and the anthrax disease. Very timely. So I'm going to move away from the history of microbiology now, and that was not all by any means of what is out there, but I thought it was a good little bit of start. And I want to talk a little bit about the implications and applications of microbiology, and I'm going to begin very broadly. That is to say that without microbial life, basically all biogeochemical cycling of nutrients would cease. So essentially all of us would die and nothing would even decompose. So that paints a pretty bleak picture, and we can broadly say that this is because they do things like fixing nitrogen. Only bacteria and archaea, the quote-unquote prokaryotic world, is capable of nitrogen fixation. They replenish atmospheric oxygen. We tend to credit plants with that, and all due respect to Kenda and, is it John? Who's the other botanist? Anyway, all due respect to you guys, it's not just plants, right? There are photosynthetic microbes as well that are responsible for around half of the world's oxygen. So they also decompose, and not only the fungal world, but also other domains of life or other archaea and bacteria. But decomposition is an important part of the role that they play in the cycling of nutrients. So this is a pretty big deal, but perhaps some of you maybe get a little more jazzed rather than about biogeochemical cycling, maybe about some other things. And I know that Holly, you said you really like to cook, right? Are you here today? Yay! What role just comes to mind right off, do certain microorganisms play in cooking? What are some things they do? Okay. Yeah, good. Okay, so one of the things in food that they do is to cause food spoilage. So they can be the spoilers in food, absolutely. What about good things? Yeah, they ferment. I mean, come on, you guys. Without microbes, there would be no more beer. It's Friday. No more beer. So this is a pretty big deal. I mean, the multi-billion-dollar organizations that are behind fermentation. Now, it's not only fermentation, alcoholic fermentation, but what about lactic acid fermentation as well, right? Cheeses and sour cream and buttermilk and all of those probiotic foods, right, that have good bacteria in them. So there's a lot of economic applications, and let's face it, they've been around for a really long time. Dating back to 2100 BC, the Egyptians began baking bread using Saccharomyces cerevisiae, baking yeast, right? Also, we saw them starting to brew beer in 1500 BC. So this is something that has been happening for a very long time. I was really fortunate the other day to get to go see the mine exhibit in Denver at the Museum of Nature and Science, and they were brewing a weird kind of fermented cocoa beverage. It's pretty cool, right? All the way back, even in our neck of the woods, we see that sort of thing. And not only do these good bacteria, say in lactic acid fermentations, cause the really great tastes and textures that we like in yogurt, for example, but they also preserve the food because they're making stuff like lactic acid, and so that lactic acid suppresses the growth of those things that make your food go bad. For example, salmonella quavers in the presence of lactic acid, so you're not going to get that kind of foodborne illness from eating yogurt or sour cream because it is preserved by the good bacteria in there. So probiotics, once again, these are very important health benefit bacteria, but also they help preserve the food, not only help you with your health. Now, I think John, last name, bioremediation, help me, are you here? Yeah. Oh, you're the John. Good. That's right. I have to get my John straight. There's a lot more than one of you guys. Okay, good. So bioremediation-wise, tell us about that. What is it, first off?
Just breaking down using microbes. Like, for example, when they had the huge oil spill down in the Gulf of Mexico, they're using
Bioremediation, yeah.
So you break down the oil essentially by a safer method.
Yeah. So if you guys couldn't hear, he was just mentioning the use of bacteria to break down oil. For example, in the Gulf oil spill, there were, for example, alkanivorox, which actually breaks down alkanes, right? It gets its name from that. So breaking down other hydrophobic oil compounds, bacteria will eat them for dinner. I mean, how rad is that? Like something that looks at oil and it's like, woohoo, dinner. And that's just rad. So these guys will break down crazy compounds. And I wonder, John, I don't know how much you know about this. So destroying dangerous chemicals, just eating them for dinner. It's crazy, isn't it, to think about TNT or trinitrotoluene as seeing that as dinner. But there are bacteria that will convert TNT into TAT, triaminotoluene. And, of course, that is not explosive. And so this is a great form of bioremediation. And I don't know if some of you chemical engineers, we have a huge number of you, have you guys heard about what happened very close to home? Anybody recognize this? It's the green belt. My athletes recognize this. They look at it and say, oh, God, intervals, mile repeats. So this is a great example of bioremediation because what happened is between 1928 and 1982, the railroad sunk 10,000 gallons of creosote in the ground right here. And so that is the oil that's used to preserve railroad ties. And so the engineers came onto the scene and in the 80s, and they said, oh, let's flush it out of there. And they tried to construct a dual drain mechanism to like push it up and out mechanically. Didn't work. So they turned to something that we call phytoremediation. Phytoremediation is a form of bioremediation because bacteria like to live in the roots of plants and grow up to high concentrations in those areas. And so by fostering the growth of those oil-eating microbes in that environment, they've been able to get rid of the oil that's sunk in the ground there and turn it into a pretty nice bike path. So that's a pretty good, close-to-home example of bioremediation. So the use of microorganisms to destroy dangerous chemicals. And lastly, many of you interested in medicine, and another application of microorganisms in medicine is that they do produce antibiotics. So the production of antibiotics is prevalent within soil. So if you look at a soil environment and you take about a quarter-sized piece of a nice moist soil, a healthy soil, you'll see somewhere on the order of 10 to the 8th bacteria in that 1 gram of soil. Isn't that crazy? Teeming with life, right? It is so full of life. And so when you think about that, those bacteria are going to do a lot of what? If it's that crowded, think they're going to compete, right, for the resources in that environment. And part of competition is secreting compounds that kill off their competitors. So antibiotics help them to dictate the species composition around them. They actually literally are kind of like bacterial machine guns. You know, they kind of kill off what they don't want there, and they leave what they want as their neighbors. But it's a little more complex than that because we're now understanding that antibiotics even act as communication molecules. But in fact, the antibiotic secretion in the soil is prevalent, and that's originally where we isolated penicillin. So penicillin comes from a mold that lives in the soil, penicillium. So antibiotics come naturally from microorganisms. So we come then to a topic that we're going to spend just a little bit of time discussing, and this is genetic engineering. And I think, oh, I'm forgetting your name. Had a fascination with genetic engineering, wants to become a genetic counselor. Help me, C, it starts with a C. Kaylin. So tell us a little bit about what genetic engineering evokes for you. Like,
they're finding certain things can be treated by treating a gene
that
causes it.
Yeah.
So, like cancer, Alzheimer's.
Right.
Pretty much, they're finding a lot of conditions now. So.
Yeah. So in case you guys can't hear what she's saying is that there's a genetic cause of certain diseases. And so if somehow we can target the gene and change that in some way so that the disease will not occur, that is genetic engineering in one form, right? And gene therapy is what she's describing. So in a simple definition, we could call genetic engineering as quite simply the introduction of genes from one organism to another organism to give it new features or abilities. Now, I talked also with one of the poster groups about their potential project, and they were thinking a little bit about genetically modified foods, GMOs. So GMOs are those food products that have a modified genotype because of genetic engineering, right? They've had genes introduced to them from another source. And we talked a little bit about the kinds of ways that introduction could take place. In the lab, we do a lot of genetic engineering. You guys will get to become, you can go home this weekend and tell your parents that you are going to become genetic engineers because you are going to actually take a gene and transform E. coli, the bacterium, with a gene that makes it glow. So you will make E. coli glow with genetic engineering. That's something that we do a lot in the lab. So microorganisms can be engineered to produce new things. Insulin is one of the most famous of those things. Insulin can be made hand over fist by E. coli. You can actually give it the gene that encodes for human insulin, and it can start pumping out a lot of insulin. We can then purify that insulin from E. coli, and we can use it to treat diabetes. Right, you bet. So this is an important application that's already well in the swing of things for genetic engineering. Microorganisms can also be modified to produce vaccines. For example, we can take away the gene that causes the disease in an organism, and we can introduce that organism, causing your body to think that it's seen the harmful pathogen. It mounts an immune response, but it's mounting an immune response to a false threat because we've taken out the virulence factors from that threat, and we've made your body respond to it so that the next time it sees it, then it will respond in an effective way. So that's what a big part of what vaccination is. Bacteria can also be used to genetically engineer plants, and that's when we talk about those GMOs, maybe tomatoes, potatoes, right, that have gotten some sort of gene delivered to them that maybe allows them to produce their own pesticides or their own insecticides. And it's interesting to note that we use a bacterium to do that. It's a bacterium called Agrobacterium tumefaciens, and it is a bacterium that likes to infect plants and transfer tumor-inducing genes to the plants. Well, we take out the tumor-inducing genes from the bacterium and give it insecticide-producing genes, and then let the bacterium infect the plant, and it passes over insecticide-producing genes, and then the plant can protect itself, right? So this is how GMOs, often using the microbial world, are made. And then lastly, we see gene therapy, right, as this sort of cutting edge of can we treat human diseases? For example, can we direct a gene to T lymphocytes in order to cure leukemia? Right? There have been some uses there. We've seen some ocular diseases that have been effectively treated this way. Unfortunately, gene therapy has not been super successful. It's kind of like the car that won't really start. Does anybody know why that is the case? Why haven't we seen, like, oh man, every genetic disease is now treated with gene therapy? Hit me.
Is it the same idea behind like rejecting an organ?
Yeah.
Yeah.
Yeah, excellent job. And I forgot your name. Sarah has a fantastic answer, because your immune system, especially if you're trying to treat a disease, let's take cystic fibrosis as an example, right? This is the lack of a particular transporter within the lung tissue. And so if you suddenly try to give the genes to that tissue to express that particular transporter, it's like your body's like, whoa, what's that? Foreign invader. And it mounts an immune response to it. So a lot like, I love your analogy of rejecting an organ that doesn't look familiar to it. And so because of our immune system, it's very hard to have really successful gene therapy. But it is definitely something that is worthy of your attention and is still a very, very active area of research. So very good answers. Now, on the other hand, some of you are pondering right now, I imagine, this very question. Yeah, Rachel, genetic engineering is real cool, but what about some of the scientific, philosophical, moral, ethical questions that surround genetic engineering? So we need to devote at least a little bit of time to this question. Any of them coming right to the top of your head? Anybody already pondering this right now? Yeah, Brett.
When you genetically engineer something
Mm-hmm.
to make it like superior,
Mm-hmm.
it just becomes like the only competitor out there, and you lose genetic diversity.
Perfect. I probably couldn't have come up with a better first statement or question than that. So when we genetically engineer something and we create something that we might call, and I love the way that you called it genetically superior, and then it becomes a monoculture. So we get for example, all of the bananas out there are all genetically identical, right? The banana that we like to eat is the Cavendish banana, and it is a monoculture. Right? It's all genetically engineered. I love to say that way, to be genetically superior. And suddenly we have a monoculture, a banana. So we lose biodiversity. So I love that. I'm going to put that. So lost biodiversity. It sounds dramatic. Good. What are the risks then, Brent?
Well, when you lose biodiversity, like there's nothing, like say some new disease comes and hits all the banana crops, like
Yeah.
there's not going to be any bananas to survive.
Exactly.
All the bananas.
Good. And you just summarized a thing that happened. The fungus, Fusarium, wiped through the Cavendish banana population and in some areas completely decimated it. So when you lack biodiversity, you can see a fungal pathogen, for example, where you have complete decimation of the population because there is no resistance, inherent resistance to disease. Typically in a population around 10% biodiversity, about 10% of the population would live, but if it's a monoculture, that's not going to be the case. Okay? So we lacked out biodiversity. We can say, let's just say something like pathogen susceptibility. That's definitely a very pertinent point. Anybody want to shout out another one? Maybe one that's very connected to this consideration. Megan.
I think the lines will begin to get blurred really quickly between what could be considered necessary and what considered,
Genetically superior for one reason or another. Yeah. Yeah, right? Okay. So when we start talking about something that we call germline gene therapy, germline gene therapy means that we are making genetic changes to the gametes or fertilized ova. And in that case, we are making changes before a baby is born. Now, what is one reason that we might maybe somebody could say legitimately we might want to be able to do that, because what kind of disease could we treat, Amy?
Like Down syndrome.
Okay, good. Okay, maybe we would say we wanted to treat Down syndrome, or what else? Tay-Sachs disease, right? And fatal neurodegenerative disease. I don't think there's any of us out there that would argue that being able to treat that disease would be a great thing, right? Tay-Sachs kills children when they're very young, and it is inevitably fatal. But what question starts to arise there, I think what Megan is bringing up, is what happens potentially at that point is, oh, yeah, so maybe we decide that we want children with blonde hair and blue eyes. But to me, that's less scary than what might we decide? You know, we can all, I mean, we're probably all on board, right? The Tay-Sachs is a disease we should treat, right? If possible, we should do this, right? With germline gene therapy. But what might we not? What might we argue about? Yeah.
Well, I mean, like, it's a great thing to, like, get rid of it, but it's like, we fix that problem, and, like, overpopulation is already a problem, and so, like,
Right. Sure.
Like, that's, I mean, of course they should
Okay.
I'm not saying
Yeah, yeah. No, right, okay, so the question of, that does come up though, right? It's a conversation that we could have as to, some people like to call that the are we playing God debate, right? And that certainly is something that arises. And you guys can jot that down as a question if you want to too. I actually want to go somewhere a little bit different. We'll say, okay, Tay-Sachs, it's a disease, right? But somebody brought up, it was Amy, brought up Down syndrome, right? What else might we bring up? Yeah, Anne. Oh, now she's raising a whole nother question. We're going to go there soon, because that's really important. Yeah. Yeah, okay, good. Super athletes, right? But what else is something that some people might call a disease and others might not? Yeah, you bet, right? When do we say, okay, You know, we're going to distill homosexuality, right? Queerness. We're going to distill that down to a gene, and we're going to get rid of that, right? Or what about being deaf? How does anyone know someone in the deaf population? Okay. How do they feel about that? Probably depends on the person a little bit. But in some cases, you know, disability can be an identity, right? Certainly, queerness is an identity for us, right? So that is something that we have to ask. What about, we come back to Brent's question, don't we? Do we want to lack biodiversity? And I think that is a worthy question for you all to ponder on this beautiful Friday, right? About whether any of this ever gets us to that question. And this differs, I think, a bit from something that we call somatic. And this is where we were talking about cystic fibrosis. This would be the idea of trying to treat an adult disease with a gene therapy. So into an adult tissue, could we bring in that gene to treat that disease? Not germline, right? Not before the child is born. So this is a little bit different kind of gene therapy, maybe less contentious in some ways. Okay, Anne, I promise. Whew, this is another big one. She just brought up, who owns genes? I had the joy of listening to a patent lawyer talk the other day at a faculty meeting and talking about what genes you can patent and what genes you can't. It's a thing. So what about Monsanto? They own genes. And what happens if you're, who's in agriculture? What happens if your Monsanto BT corn escapes and somehow plants itself somewhere else where it's not okay? Big trouble, right? So who owns genes is another question that comes around with that. So when we decide that there's a genetically superior BT corn, it is the thing, right? We all want to plant a big old monoculture of BT corn because, man, it produces lots of food, because it produces its own insecticide. So let's all plant BT corn in monoculture, and Monsanto owns the genes, right? It's an interesting thing to ponder, okay? So I'm going to leave this for here. Is there anything else, anybody, just really another question you want to shoot in here? These are all super important questions. Okay, yeah, Bridger.
Who gets gene therapy?
Oh, God, such a great question, right? I mean, this is fantastic. You guys are amazing. You're rocking my world. So who benefits? And I think we can probably somewhat answer that question right now. Right? Can we answer that question? Who? People with money. And in fact, we can broadly state that technology widens socioeconomic gaps. It's a thing. We know that. And so the people with money, those are the people who might get the benefits there. We widen socioeconomic gaps. The people who are disadvantaged only become more disadvantaged. Okay, great. Okay, great, right. So what about the fact that we just can't quite predict what the effects are of all of the changes that we might make? Absolutely, unforeseen mutation. Also, what about the idea that we can't be certain of lateral gene transfer between a genetically modified organism and an organism that hasn't been genetically modified? Perhaps seeing those genes being transferred, say the pesticide or insecticide genes that are passed from a crop in a field of monoculture corn into the weed population. And then you start thinking about super weeds. Oh, how about this, guys? What about the insect population? What is happening to that population when all of the corn produces one insecticide? What are we doing to that insect population? We are selecting for those insects that are resistant. Okay? We can think about how well that's gone with antibiotic overuse issues, right? Selective pressure put out there will inevitably select for resistance, okay? And we'll see a population grow up that is resistant and being selected for. I'm going to jot down before you leave here and you get my social calendar. But yeah, let's make sure we put out there selective pressure. Absolutely. Thank you for such a sexy-minded Friday discussion. Have a wonderful weekend, and I look forward to seeing you all on Monday.